So, in today's video, we'll discuss on numerical problems, solve problems from Salient pole synchronous machine. And what I told you that if you want to enhance your own problem solving ability, what you can do is that you can copy the problem on your worksheet and then you can proceed. So, let me just copy the problem first. Three phase star connected 1.5 MVA 6.6 kV alternator has 9 slots per pole and 6 conductors per slot. Axle drop is 10%, resistance drop 0.5%. Both are obviously recorded during full load condition. Actually, I am not copying the exact problem because that will consume more time. Now see, the rotor has this problem will solve in the line of cylindrical rotor machine, although this is a case of salient pole machine. Rotor MMF may be considered as rectangular base being 3/4 of the pole pitch. So we have to find out the approximate exciting current approximate value of exciting current required and regulation with full load 0.8 power factor lagging, right? So just let me check whether it's recording or not. So this is the detail of our problem. Uh, have they mentioned about pole? Okay, another few data are given. Uh, that is that iron means all the constant loss, iron friction windage and mechanical loss, all their aggregate loss is 40 kilowatt. And also field coil voltage for rated field current is 180 volt. We need to estimate the efficiency for this operating condition. So from here we will get the current, and here 180 voltage is applied across field coil. So from that you can figure out the amount of power you are means actually applying to produce your field uh, coil. Now the data for OCC, data are like this. This is in ampere, this is in volt. So this is all the data that is given, that are given data. Now no information about individual value of xd and xq, but we need to find out the means regulation. So how can we proceed? Do remember that open circuit and short circuit, all these are free from your means direct and quadrature axis reaction. Like if I can show you what I want to show you here, that if you are not trying to draw this like this xd and xq, rather you keep e dash, means after drawing e dash you do not try to find out e dot or e dot dash from this e by adding some vector, then perhaps you can construct the phasor diagram without having an explicit information regarding xd and xq, right? Like what I am trying to say once again, that if you sorry, if you know only here r and xl is given in our problem, but nothing is mentioned about xd and xq, they are separate value of xd and xq. So what we can do, we can take the help of the theory that we are practicing in cylindrical rotor machine, and see how we can apply those theory here to solve our salient pole synchronous machine. Right. So first of all, let us be very good, means let us try to find out the terminal voltage. So what about base impedance? Sorry, sorry. Now R in per unit value will be how much? Oh, sorry. Just a minute. That R, this value was given in per unit. So what would be this one? This will be XL per unit was 10%. So this XL actual value will be so. With the help of this, now try to understand what I was trying to tell you. Let me go to the next page. What we can do here is that we can just draw the phasor diagram in line with our cylindrical rotor machine, because no specific information is given. So but still we can draw the phasor diagram like. Drawing this doesn't require our knowledge of XTXQ, right? Now for E, we can draw a line that is proportional to FR. Then let us draw minus a, and from this f naught we can draw e naught, making an angle 90 degree with f naught. Obviously, this fr will make an angle 90 degree with your this one. This fr will maintain 90 degree with e. Now see that explicit information about xd and xq is not required, and I'm not even violating things, because as long as we are doing it here means we can do this with a fair enough approximation. Now uh, once you get this detail, or means draw this phasor diagram, is where x dx q are required, when you need to draw something like this. Means when you are trying to represent armature reaction MMA by means of a virtual reactance, then only you need xdxq. This will become jxdid, this will be jxqiq. Otherwise, it is not required. So, if it is not required, then see what manipulation we can do here is that we can write the equation of E like V plus I cos theta minus j sin theta, since lagging load. So this will be here, as this book is doing everything in terms of actual value, that is why I am not using any per unit value here. However, the whole problem can be done in per unit basis also. There is no harm. In that case, you just need to do everything like this V will become 1, current I will become 1, and these people will become 0.005, and this. Even we can check whether we are getting the correct answer or not, although that would be a very daring step from my end because I am very poor at calculation, but I would like to show you that. Now see, just for our information and just for checking that whether per unit gives us the same result or not. So what we will get, just a minute, let me do the, okay, so since it gives us correct values, so it's good that we are getting the correct values. Now, like what we can do here is that we can check that 1.066 into our base value 3810, how much we are getting. We are getting 4061.46. So means more or less 3 volt difference in the scale of 1000 volt. It's negligible, right? So it's very clear that we can go for this one also. Anyway, let us consider this actually. So if you consider this one, then what will be your line voltage? Now, your from the data of your induced EMF and line voltage, that is here, from this we need to figure out that what the value of this one is 7039. So it will fall somewhere between these two. Like if we try to draw the OCC, then it would become better one. So let me just search that whether we can get some OCC. Yeah, this is the same OCC. Just a minute. Just a minute. Well, so if we plot, we get a curve like this, right? Now see that here we are getting this value. Uh, it is interesting to note that from this curve we can actually figure out many things. What we can figure out from this curve, that for this value 7039 volt, uh, 7039 means let us consider it as 7000, so it will be somewhere. So as per the book claim, it is 28.43 43 ampere. The amount of means field current is 28.43 ampere. Now, if it is 28.43 ampere, then it is happening here. Then what we can do, that we can use the phasor diagram that I draw here. Like here we have got, if R is equal to 28.43, if we can figure out A, then means although this is better suited for your, like, your cylindrical rotor machine, because one shortcoming with this diagram is that here I am assuming that A is facing, or armature reaction MMF is facing a constant path, which is actually not the case. Here armature reaction MMF is not getting a constant means reluctance path, rather its reluctance is variable in nature, but still that is means good approximation, won't cause much problem. So just a minute. To proceed with, let us calculate the armature reaction MMF. The fundamental armature reaction MMF will be, these are for rotor. So this will become number of turns per pole will become KB will be, we are assuming 60-degree phase spread, so KB will be 60-degree phase spread. Okay, let me do it, otherwise you will not get it why it is, how it is coming. Like if you practice then you will get, but otherwise not. That number of slot per pole is 9. So number of slot per pole per phase will be 9 by 3 is equal to 3. Now if you assume phase spread is equal to 60, that means 3 stator means slots are occupying, rotor slots are occupying this 60. So 3 into slot angle is equal to 60 implies slot angle is equal to 60 by 3 degree, that is 20 degree. So if it is 20 degree, then what it would become? It would become KB is equal to so if you do it, you will get 0.96, which is very common. And as nothing is mentioned, we will assume Kp is equal to 1. So with this, let us calculate. What we will have here is that this person, we know this will be sorry, this is not IF, this is actually IFL. So this will give us armature reaction MMF, that is 3061 ampere turn per pole, right? Now that field, see what is mentioned about field rotor MMF. Field rotor MMF is like, see what is written there about field MMF. Base being 3/4 of the pole pitch, right? So if 3/4 of the pole pitch, rotor MMF may be considered as rectangular, base being 3/4 of the pole pitch, then what is the amount of means cording here? Means rotor means MMF. This information we need to means utilize here. The rotor MMF, the common formula, rectangular, for all rectangular it is 4 pi into 150 into IF into your base being so you will get it is 176.4 IF. Okay. Now this armature reaction, if you refer to in terms of field current, you will get, let it be IFA is equal to 3061 by 176.4, that is some 17.4 ampere. Now you may ask me the question that armature MMF is being produced by means alternating current, and when I am converting it to corresponding value of field current is DC. How this is means we can convert our AC to a corresponding value of DC. Actually, it is not AC, not DC. First of all, it is MMF, and that MMF, although it is like MMF is rotating in space, and the DC current carrying winding is rotating in space. If you remember, a few days back I asked a question in your group. One student answered it. Tanish, probably his name. He said, my question was that field MMF is produced by direct current, and armature and all voltages are rotating at some means alternating with a frequency of say 50 Hz. So how can we put them together in a single phasor diagram? He said, and it was very correct observation, that field, it is produced by an alternating current, but it is like means this field it is rotating in space. So DC current rotating in space will produce a kind of alternating action with respect to a stationary winding. So a stationary winding carrying AC current and a DC current carrying winding that is rotating at the same speed of synchronous speed will means have same frequency with respect to a means neutral observer or means an outside observer. So that is why we can means draw them in a single phasor diagram. And applying the similar logic, we can use this kind of unitary method to interpret the amount of your armature reaction MMF in terms of your field winding. So basically what is this 17.4? This is basically this minus A is 17.4 ampere. Now what we need is to figure out this angle. How can we figure out the angle between means this angle we need to figure out angle between FR and A. How it can be we can find it? We already know that it is 90. If we somehow measure this angle which is already here, that is 4.13, and this much is how much? Cos inverse 0.8. So angle between A and FR is how much? 90 plus 4.13 plus 36.86. So you will get something like 36.87. You will get something like 131 degree. So we need to utilize this information here to calculate our F. So that will result us something F is equal to 41.9 ampere. Therefore, the field excitation necessary is 41.9 ampere. Now for 41.9 you can again figure out the corresponding voltage, and from this you can figure out E naught, like 41.9 somewhere here you will get, and that voltage will be something like, as per their calculation, it is okay. I just draw it slightly, means at 40.5 it is not that. So 41 means almost 41.9 means almost 42. So it will be like Now regulation will be how much? So what about output? This is full load MVA. This is load power factor. So, okay. So what about armature copper loss? Sorry, this should be in megawatt or kilowatt. Now already the constant losses are 40 kilowatt. So total will be how much? Okay, then field loss. How to find out field loss? 180 volt into this much current 41.9, so that will be 7.54 kilowatt. So percentage efficiency will be 1200 divided by 1200 plus is 7.49 plus 7.54 plus 40 into 100%. Whatever you will get, it is 95.6%. So this is interesting. Now we'll check the result using ASA method. ASA method is also applicable to Salient pole synchronous machine. We will do it with ASA method. So now, as I have said, that ASA method can be applied to for finding regulation for both cylindrical and Salient pole machine. But before we start with ASA method, let me just quickly draw a few figure that was there in ASA method. Like I think they are present in our previous discussion. Just a minute. I think they are very much there in our previous discussion. Yes, this one. Uh, this diagram. Okay. Let me just copy that diagram from somewhere. So now we'll see that how we can use this one. This basically here we need to find out using this means ASA method. As a method, what we need to figure out that your A plus AX. What is the amount of A plus AX? That is the amount of field excitation required to circulate short circuit current, full load short circuit current. Let me write. Should be compensated. To circulate full load short circuit current, right? So here what we are assuming. So what is your means short circuit uh, means value of E is during short circuit, this is the scenario. So what it will become 2.9 into 2.9 is the XL. Actually, let me write it in correct way. Now convert it in your line. So now we need to figure out that how much current is required to produce this much line voltage. So here 659. So say this much is 1000, this much is 500. So somewhere here, as per this book, it is 2 ampere. So corresponding value of means your corresponding value of I F is 2 ampere. Now, what is your armature reaction MMF? We have already computed that much. Armature reaction MMF is 17.4 ampere, right? So here, actually this is giving us this much you need to compensate your AX, right? But what about A? A is proportional to 17.4 ampere through your field winding. So A plus AX will be how much? 17.4 plus 2, that is 19.4 ampere. Correct? Now if this is 19.4 ampere, now we need to figure out value of MMM corresponding to 6600 volt. So 6600 volt, I think that was also often somewhere here. Okay, nowhere. So for 6600 volt, it will be 21 ampere. So that 21 ampere is like here. So this 21 ampere is like therefore your total like here we as we neglect IR, so what we can write that so this will give you FR is equal to 21 square plus this much is 19.4 square. You will get by doing the means taking under root of this, I will get right. So so for this 36.1 ampere, we need to figure out the means what is the voltage. So for that we will find for this 36.1 will cause voltage, induced voltage is equal to just well, now from our previous calculation, what we can see that for V, try to understand that why I am means intentionally selected this problem, because in this problem only we are means solving a problem of salient pole synchronous machine, almost like cylindrical rotor machine. Later on we will take problem that is actually we need to, there will be no such means way out for us to circumvent the means explicit occurrence of your xd x cube. But here we can somehow, the problem is framed in such a way we can avoid it. So from this what we can see is that E line is 703941.3. Now for this 7039 you need to find out this value of ff dash, that is the last part. So for this one means precisely we need to figure out this length. So this length we can see, this is approximately how much? Approximately, as per the book, this blue color length is 6.6. So see, this calculation remain valid whether you are considering cylindrical or salient pole. It is true for everywhere because your winding XL is constant. Means for given case XL is constant, R is constant, and it has XL and R has nothing to do with your means saliency of your rotor, whether the rotor is cylindrical or salient. So these remain constant. So from that we can take this value and we add this to find out the resultant means that wave dash, that is equal to now for this 42.7 ampere, again from this diagram, what you can figure out that for 42.7, somewhere here as per that book you will get for 42.7 you will get 8100. Corresponding voltage will be 8100 volt. So percentage regulation would be efficiency remains same, so no need to calculate efficiency separately. Okay, now let us go to next problem. Okay, so here means before I proceed to deal with more complicated problem, let us deal with a few simple problem. Three phase star connected, just a minute, where it goes. Yeah, a three phase star connected synchronous motor, sorry, alternator supplies a load current of. We have to find delta, that is load angle, id, iq, and percentage regulation. So here the things become quite simple. Try to draw the freehand diagram of the phasor quite often, so you become an expert of drawing phasor diagram of this synchronous machine, and it means like it get means almost it stuck to your head. So every time, whenever you need, you do not need to think about it in detail. Rather, you can figure it out that yeah, this is the diagram that we know. Now, as said, r is equal to 0. So, if r is equal to 0, we will have no IR. So, what we will have? We will have JITXT and XQ, where your correct. If we draw a line, However, this line is not very important. This angle is delta. This angle is beta. So in other way we can say if this angle is theta, then and in order to figure out this arm of this tool or regulation, what you should do is to draw a perpendicular on this, and that will yield a very straightforward relation like Vt cos delta plus xpid is equal to your EF. So now with this formula, and also we have derived that your delta is equal to tan inverse here it is Ixq by how much Vt cos just a minute, it needs us, well, the formula was, give me a minute to write it down. Tan delta is equal to IQXQ plus our we can write it in this way also. It is IXQ cos theta. We have already proved it. V plus IXQ sin theta. Right. So as xq and all these are given, we can figure it out. It will become some 8.72 degree as per my calculation. It is becoming 8.72 degree. And means not this one actually, this calculation will yield delta is equal to 8.72 degree. Just a minute, let me check the calculation. A slight correction, as per my calculation it is coming 8.41 degree, Anyway, not a big deal. You can calculate. That is the value of delta we are getting. So what about beta? Beta is equal to cos inverse 0.9 plus delta. That will give you some 34 point, say 30 degree. Now what about your ID? ID is equal to I sin beta, that is 9 sin. Now what about EF? EF is equal to, as we know, this much. EF will be Vt cos delta plus ID xd. So that will be actually the book from which I have taken this problem is full of so many calculation mistakes. Now I just, sorry, this one is, as per my calculation, it is 8.41. I made a mistake. This book compelled me to learn calculation using calculator. Otherwise, I am a person who like afraid of using calculator. So, as per my calculation, I am getting, it is something 16.99%. However, in the book from which I am copying this example, their calculated regulation value is 9.275. However, they have made a mistake in terms that they did calculation like this much is okay, but what they did, they calculated here 440 In my opinion, this is grossly incorrect because you cannot add one line voltage with one. This much is in case line voltage corresponding value, and this remains phase voltage. So this is not correct. So this answer is also incorrect. But whether I have made a correct calculation or not, that you need to check. But I hope this problem gives you certain idea how to solve a problem. Calculation you can do it by yourself. Now let me ask you a very simple question, that do you think your, like I said, xt is greater than xq irrespective of, this one is always true. So does it imply that id is always less than iq? Even our sleep test we have uh, seen that, but is it always the case, or in some cases we can have id that is greater than iq? Okay, think about this. Now another problem is given, like this problem states a three-phase 440 volt 50 Hz delta connected alternator has direct axis resistance. So delta connected alternator xd is equal to 0.12 ohm, xq is equal to 0.09 ohm per phase. If the alternator supplies 900 ampere, we need to calculate the excitation EMF. Excitation EMF is also known as but this is not is equal to induced EMF. I think I have explained it quite a lot of time, but even if you have confusion, please utilize Wednesday and Friday class. Those classes are not for means like just coming and joining a meeting. Those class should be utilized in a more means purposeful. Means we must utilize the time. We should not waste it, because I am having two theory courses. I am not giving you any lecture or anything, but if I can show you, means if I do not do any, means generally I crop videos, crop the film so that you can see that it is only the video portion is available. Otherwise you could also see right now it is. So means I also expect that you people do something anyway. So as it is delta connected, so I phase will be IL by root 3, that will be 62 ampere. Now here things are very simple. It is, first you need to calculate actually this relation is coming from where? From this diagram only. If you consider this triangle, then you will see that this height is how much. We can prove that this is 90 degree, so this will be 90 minus delta. Now as this is 90 minus delta, this one is actually what about your JIX cube, that is perpendicular to your I, means it is 90 degree. So how much it would become? This would become sorry, here not this technique is not good. Here we should draw, if we are interested to do it in terms of delta, we should draw okay, no, sorry. What was our approach? Just yeah, this is IX cube. So if we draw this will be how much? This will be 90 degree. This will be angle beta. Therefore this angle will become 90 minus beta. I am considering this larger triangle. So if this is 90 minus beta, this is 90, this is 90. So what about this? This should also be beta, right? And this much is how much? This is our Vt minus delta. Well, so that's great. Now what about this? This side will be, we can get it like by doing some manipulation. It will result us that tan delta. What is tan delta? That is like ix cube. How can you get delta? You need to consider this triangle. Obviously, here it is your Vt cos delta plus you am having here ix cube beta. So from that we can figure it out that this relationship, right? So now with this relationship, quite often try proving this relation from different perspective, different angle. So that will enhance your understanding. So this time your ix cube. So what is I? That is 519.62 into your x cube is how much? Your x cube is 0.09 into cos theta is 0.8, and this is your 400 plus 519.62 into 0.8 into your sin theta is 0.6. So that will become, just a minute, let me calculate. Point 0.09 into 0.6. It is giving us delta is equal to 4.99 degree. Right. So if it is 4.99 degree, then you can figure out ID and IQ. So let us figure out ID and IQ. ID is equal to I sin beta is equal to your 519.62 into sine of how much? It is 36.86, that is your theta, plus 4.99, that is your delta. So it will become 346.74 ampere. IQ will be how much? Can we use this? Obviously we can use this. It is simple sine cosine relation. So why I am showing you this? Because we may use this relation also. So it is 387 ampere. So why I am telling you this? Because if you calculate like short circuit test, and from that short circuit test, if your VT, let me tell you one problem, that VT and say your XD is given, means this problem is not available in book, so I cannot share you the numerical data. I am trying to frame the problem. Try to listen to me. As we know that from short circuit characteristics for salient pole synchronous machine, what we can figure out. So if things is like that, like your XD is given, VT is given, right? XD is given, VT is given. Obviously, in case of short circuit test, what is your VT? VT is equal to 0. Now, just a minute. I just frame that problem. Yeah. Say okay. Forget about means XD. Leave it. Say OCC and SCC data is given. So if those data are given, then using them, what you can do, you can figure out like that value of XD what is value of xt? Value of xt is equal to your just like synchronous machine. Short circuit, same field current. So if that is our case, then we can figure out our xt. Now what is asked in the question? The question, it is asked that your like your for a given load, your theta is given, theta and current are given. Now in addition, your percentage regulation is also given. So from that you need to figure out xq. So obviously you should not have any difficulty in finding out xq, right? Like how to find out xq? ef is equal to this vt cos delta plus idxt, right? Now obviously here xt you do not know, but sorry, id you do not know, but here it is like okay, just keep this problem. I will tell you that what to do. Actually, let me give you some hints. Here if we say neglect armature resistance, as of now we have not yet discussed, but later on I will show you that for r is equal to 0, basically we can show that 3VE sine delta by your xt, that is some formula, is equal to 3VI cos theta. Whatever power is consumed, that has a direct relationship with our means this your VE and xt. So from this we can figure out the, since the load, current, terminal voltage and everything is known, as well as power factor is known, percentage regulation, you can figure out E also. So from that we can find out the value of delta as well as x cube. I'll show you. Just keep this problem in your mind so that in later stage, once we discuss the power flow equation, we can solve this. Okay. Now, well, as of now, we are discussing or trying to find out like our regulation using formula B, means beta is equal to delta plus theta. But can we do it in terms of beta directly? And what about percentage regulation if R is present? In this problem, I'm going to show you that. Once again, let us quickly draw the phasor. This is our beta. Now, here we have IR. Let me draw JIDXT. This is JIXQ. Well, now what about this triangle? If we try to draw a triangle at all, that is parallel to this EF line. The base of this triangle is parallel to EF, and height is perpendicular to A. So obviously this height of this triangle, this is will form a right angle triangle, is parallel to JIQXQ, and the base is perpendicular to this JIQXQ. So if it is JIQXQ, that means this one is can be written like IQR, and this side is IDR. So let us draw projection of IQR. Now this much is how much? This one is VT cos delta. This part is IQR. This part is IDXT. Now let us draw means this line. So this is 90 degree. This much is your beta, and this is 90 minus beta, right? So we are now at this moment we are cautious, means interested to find out beta. So for finding out beta, what we can write, try to understand that this one, this triangle, if you consider, means this one. If you consider this triangle, this is a right angle triangle. Now what is the hypotenuse of this right angle triangle? That is IX cube. So what about the base of this right angle triangle? This much will be so this will give you sin beta. So what you are having here is that yeah, now what about cos beta? Like this one will be how much? Or what we can do is that we can write this VT like this angle is how much? This angle is theta. So we can write In other way, a projection on this eye line can be drawn. So this much will be Vt cos theta. This side will be how much? This side will be Vt sin theta. Now for this triangle also, what you can do is that you can write Vt cos theta, the base of this triangle Vt cos theta plus IR. This is this arm. Vt cos theta plus IR, and this side is how much? This side is your Ix cube plus Vt sin theta. This much is Vt sin theta. So we are having a triangle like this. This is Vt, this is theta, this side is Vt cos theta plus IR, and the other side is this angle is beta, this side is Vt sin theta plus x cube, Ix cube. So we can write that tan beta is equal to Vt This is also an important formula. So here what is our Vt? Our Vt is, in this case, is 400 by root 3. So it will become, if you do the calculation, yes, sin theta means here 0.6, here cos theta 0.8 plus so that will yield beta is equal to tan inverse 1.3475 is equal to 53.42 degree. So ID will be actually, before I means you give the answer in this problem, we got our answer which I asked you in the last problem that can we have a situation where ID is greater than IQ, but still I am looking for a more conducive answer, like a kind of case study from you, that okay, for this kind of load, this type of load, we can expect ID to be greater than IQ. Okay. Now here, just a minute. So what about your excitation voltage, EF or whatever? That will be V cos your delta plus IQR plus IDXT. That's what I was trying to tell you. This total side Vt cos delta plus IQR plus IDXT. So here if you keep means providing the correct values, obviously here this will be 53.42 minus cos inverse 0.8 plus IQR, that is 8.6 into 1 plus ID 11.59 into 15. So that will give us 404.33 volt. So line voltage will be root 3 EF, that is around 700 volt. Okay, so after that we will try some more conceptual problem. Now in this problem we will study the effect of saturation on our salient pole synchronous machine. The outcome of sleep test is given like xd is equal to 100%. It is all per unit value. xq is equal to 80% and resistance R is equal to 1%. We have to determine the regulation at 0.9 power factor lagging. Right, and XL is 10% and the OCC has to be taken from the OCC. Let me share the OCC. No. Okay, just a minute. Now, yeah, just a minute. So this is the means picture, right? So from this, we need to calculate the regulation while considering the saturation factor. Now, I have not yet discussed that how to take care of this saturation factor when you just need to solve this kind of problem. First of all, we must understand that, well, you may argue that this is the image we used for dealing or rather describing a cylindrical rotor in synchronous machine problem, but it is not a big deal because in your machine it's like all these characteristics OCC, SCC and zero power factor, they are actually free from your quadratic means q-axis representation. Even if you are having some difficulty in digesting this fact, try to understand that OCC, forget about OCC, because in OCC neither XD nor XQ has anything to contribute here. And you can also understand one thing, that in case of XD, or means not XD, rather you consider the air gap along direct axis, whatever air gap along direct axis you will have. And for cylindrical rotor machine also, the air gap, what is the difference between cylindrical rotor and salient pole? In cylindrical rotor, the air gap is even. In salient pole, the air gap is non-even. Along direct axis, it's small. Along quadrature axis, it's large. But what about cylindrical machine? Cylindrical machine air gap is even, and that even air gap is quite close to your direct axis air gap for salient pole machine. So, what type of means characteristics you will observe during OCC for your quadratic, sorry, for your salient pole and for your cylindrical rotor, means your OCC curve will not be affected. Because if you means think about more, as I have said in my earlier lectures also, that it is only the armature reaction that can realize the difference in the path permeance, or therefore it is giving the birth of two virtual reactances, one is XD, another one is XQ. They are not real and they are only experienced by armature circuit, not by your armature reaction, not by your field. If you consider yourself as an observer who are sitting on any of your pole tip, or means any of your means where the field are embarked on your pole structure, and you are someone who is sitting on the pole tip, you will see that the air gap is even in nature from that field. So on OCC card, whatever is for cylindrical, the same type of nature you will get for your salient pole machine. Talking about SCC and jet power, zero power factor. In case of SCC and zero power factor, also in case of SCC also, if you disregard the aspect of armature resistance, what you will have? You will have your armature current, full load armature current lagging your terminal voltage, or means whatever your voltage you are having, E induced EMF, by an angle 90 degree, right? So if it lacks the voltage by an angle of 90 degree, then it of course make perfect sense that this one, like this whatever we are talking about, is and also try to understand one thing, that once you disregard R for a zero power factor armature current, your V and E will become a collinear phasor. Think about it. It is your, what I am trying to say, this is V, this is I. Huh? Now, what about your E is equal to V plus IR plus JIXL. Now, if you drop this term, what remains? This JIXL. What would be its magnitude? In this way only. So, this total will become E. So, E and V will become collinear, right? So, it is very clear that uh, whether it is your SCC or your ZPF, if you disregard the armature resistance, E and V are two collinear phasor, and the armature current is lagging that same phasor by an angle 90 degree. So, if the current lags the voltage by an angle 90 degree, then how it would affect, what type of armature reaction it would produce? Pure demagnetizing action. And pure demagnetizing means, if you think about your field structure, pure demagnetizing action means try to means imagine this situation like your, this is, say this is your field structure. So say this is your armature structure. The outer one is armature structure. Now, that armature current, if it is lagging, then what we have already studied, so what it will produce? It will produce for zero power factor, this is your D axis, this is your D axis, this is Q axis. Now what about your uh, virtual armature magnetic field produced, means magnetic field, you can visualize them as produced by a virtual magnet. If this is N, this is S, then for it purely lagging current, that is lagging your E by an angle 90 degree, it will be like Sn. So it is just demagnetizing and it is acting along your XD. It is free from XQ, means it is not able to produce any kind of XQ. It is totally XD. So if it is totally XD, then uh, we can utilize a curve which was for cylindrical rotor valid curve, a kind of similar curve we can get for our salient pole machine, and that is not a very surprising thing. Now come to our particular problem where we have to figure it out using like one more information is given that our like although everything is there, but 100% voltage is equal to 11 kV. This much information is given. Okay. Now, before we discuss Kingsley's saturation factor, which one problem we have dealt with a factor K, that is actually Kingsley's saturation factor. Now, first of all, let us try to draw the phasor diagram of a salient pole synchronous machine considering saturation. What we'll get? First of all, we have to decide that between D and Q, which axis will be saturated. Obviously, it is the D axis that will be saturated. Q axis, or better to write, will remain unaltered because of large air gap. Right. So now let me draw the phasor diagram for that saturated generator. Obviously, here, what do you expect? How can we proceed? See, for our ready reference, let me just copy that what was there in our unsaturated case. It was like now IR, given we know JIXL and JIXQ, what I taught you, if you could recall, it was like this is JIXQ, while this is our E, that is JIXL, and then just a minute. This was JIDXT. This much was JIQXQ. We studied different formula for also, but what I told you that at the beginning, as we do not know this much, that is delta, and this angle is theta, and obviously what we know that beta is equal to delta plus theta, but initially finding delta is difficult. So I told you that what you can do, if we need to construct the phasor diagram, we can go and add V plus IR plus JIXQ. This will result of phasor say E dash. This E dash will become a collinear vector with E naught, where E naught is your unsaturated, or you can denote it by E1 also. So E1 is something that is vector collinear with E naught, where E naught is your unsaturated induced EMF, right? So this like, yeah, it's unsaturated induced EMF. Now this phasor E1 actually determines what? If we further write it, what happened? Okay. If we write it here, we can see that this E1 is giving E1 is equal to V plus IR plus JIXL plus JIXAQ. Right. So this much we can write. Uh, Now JIXAQ. So here, like, because we know XL plus XQ is equal to this one. So now what we can write further, we can write another thing, another voltage equation, that is your ED. What is this ED? ED is your uh, voltage that is due to, we can write V plus IR plus JIXQ, that means these two gentlemen together, plus JIQXAQ. So this last term, this JIQXAQ, if you are having difficulties in understanding this, let me draw the picture, then you will get it more clearly. So this is V, this is I, IR, JIXL, E. Now This one is how much? This one is E1, right? From this length is E1. E naught we can't consider because now our this is saturated, right? So further, if you want, I can draw the MMF also, that will become helpful. Say along this you are having A, but A actually cannot be represented. So what you will have? You will have your ID, that is acting in opposition to your field flux, right? Here we are having IQ, right? So accordingly we can have our MMF also. Let the MMF be MMF be AD, and along this it's EQ, correct? Now see that we can find out another one, that is ED. What is that ED point? If you draw a line that is just perpendicular on this, from the tip of JXL, it is perpendicular on this line of E1 or E0, then you can find out your direct axis voltage. And this ED can be written as your V plus IR plus J I XQ plus J IQ XAQ. So apparently it gives you a feeling that this is going to like this J IQ X AQ. Just a minute, I might have made a it was correct that actually I just took some time to verify that whether it's correct or not. This statement is correct. See what I am trying to do. Had we considered a case with normal one, unsaturated case, then it was having this gentleman, two gentlemen having here. So due to saturation, we will not be able to now consider this one. Means try to understand that why this saturation is affecting, because like due to saturation means after this also it is not getting reflected, your regulation is not getting reflected. We'll discuss the easier method to tackle with this, but first try to understand and you try to realize the problem. Anyway, let me explain you this one. So ED is this. When we draw a perpendicular on this, obviously this perpendicular ED can further be explained like if we just shift this JIXQ here, like from the tip of IR, if we draw a perpendicular, then what would be the height of this perpendicular? This height of this perpendicular would be IQ XAQ. So basically what we are trying to track by writing this line, V this much, IR this much, then here we need to reach. Now this length, we are trying to express this length as the sum of these two phasor. So if we add these two phasor, then they should give me this phasor, that this part, right? So we are doing it and getting our ED. However, ED is how to get ED? ED was if we draw a perpendicular from this E, we are supposed to get ED. And that is only possible when we do this, right? Now, here, when we are considering this ED, then like basically ED needs this much of extra length, right? So we are writing in this form of equation. Now what I am trying to do, that is this ED is what? This ED, if FR is your original field MMF, we can write FR dash is equal to FR plus AD, right? So this ED is proportional to FR dash, and now based on linear scale you can find out the original EMF E naught in open circuit condition. If it is like based on this proportional relationship, you can find out E naught. But this method is quite cumbersome. So what we can do is that what we use for cylindrical rotor machine, like XS corrected is equal to XS minus XL by K plus XL, that was we did, and this value of K we used to find this value of K from our that OCC curve. This was known as Kingsley factor. So here also we can do this. Now let us try to apply this here in this case to understand that how this Kingsley factor can help us to solve this problem. So once again, let me quickly copy all the details. Please don't get impatient, because this kind of problem needs time and understanding, and also I will be very happy if you ask me questions, because in this remote mode it's very difficult for me to convey to you what I am trying to say until unless we discuss. A few students are saying that they are getting everything. That's very good. It's my pleasure. I'm feeling myself blessed that having such good student in the pool. But still, like still, everyone should ask question. So here, what we need to find out, we need to find out regulation on full load point 0.9 power factor lagging uh, with all this detail given. So first, how should we start? We should start by finding E. See how this will help us greatly. So E will be how much? Now you know all the values. If you put the values, you will be getting as it is in per unit. So I is also 1. Sorry. This one is XL. Yeah, XL. Not XQ. It is XL. Yeah. So XL R. So this gives us how much? It is 1.535. You will figure out why we need these two separate information. 27.8. And what about that E1? E1 is so U1 will be how much? U1 will be your 1. Sorry. This calculation I made some mistake. It is 1.056 angle 4.67. Yes, and this one putting the values will be getting. Just a minute, let me calculate. So now, just a minute. This is going to be something like 1.535. Angle is 27.8. So why do we need to calculate these two? So that we can figure out the difference between these two angles. So Now what we will do with this angle? What is this angle? This 23.13 is this much angle. So once we can figure out this angle, then we can take this right angle triangle, and instead of doing such complicated things like V plus IR plus IQ J IQ XQ, we can do it more smoothly, like just from this triangle. This E is its hypotenuse, and this your ED is the base. So we can write ED is equal to, instead of exploiting this complicated equation, we can drop it and use ED is equal to E cos this angle 23.13 degree. E is known to us, so ED becomes 1.056 into cos 23.13, that is 0.9196. So this gives us so this in volt will be how much? Now what is this much voltage? This 10681 is proportional to Fr dash, right? Now this for this we need to figure out the value of IF. So for that we need that graph, yeah, this one. So it is 10681 volt. Ten six eight one volt. Just a minute. Oh. This is our air gap line. So from this we can figure out this 10681 volt is basically for 81, right? But at the same time we can see that this air gap, this is 81 ampere, and from this is our OCC line, right? From this OCC line, as per the claim, this one is 93 ampere. Why do we need these two? To figure out this length, right? So how this will be utilized? The saturation factor, which is also the ratio of the slope lining joint above. Like here we are telling you that how you can actually figure out Kingsley factor, factor K. Factor K is like so once we get this K, now for this one, this ED, why this ED is required? Once again, like instead of finding out ED from this complicated equation, we find it using this equation. Then what we are doing here, from this ED is proportional to our this, we took two values. Actually, if you recall, or if you can watch the video on cylindrical rotor synchronous machine, you will find the answer also there. So from this we can figure out this is our Kingsley factor. So what about our XD now? XD will be your XL, that is 0.1 plus your XD 1 minus 0.1 by your K 1.15. So XT is equal to becoming 0.8 PU. This is saturated XT. Right. So now we can figure out E naught. What will be our E naught? E naught will be this is an alternative way to figure out the means. Using Kingsley factor, we can figure out the regulation. Or alternatively, what can be done? Like here, during your operation, what your machine is getting, that is V, and ED is proportional to your FR dash. So now what you can do is that instead of finding out that Kingsley factor, from here your ED is proportional to 8.1 and this is 9.3. So you can see that this is like your, you can use in line with ASA method, you can figure out, just a minute. Okay, actually from that also you can calculate like from graphical data, but that is not very important here. What is important here is to note that this is 60%, and for your information just want to share one thing, that if you want to figure out from these, then what, think about that how means this is one way. Otherwise what you can do is that you can use that ASA and other method to calculate the regulation, and even you can tally it, right? Now perhaps we come to the, probably this is going to be the last problem of our yeah, this is the last problem. Let us do it, because the problem with this long videos is that it also consumes a hell lot of time for me and I cannot do anything else. So I am also eager to complete it as soon as possible. For a Salient pole generator, oh, all this in per unit. This is part 1. Part 2 is So in the first problem it is rated current, in the second problem it is rated power, and whenever it is zero point 0.8 power factor lagging, obviously uh, like rated power means your kVA becomes 1.25 times of your means rated kVA, because if you are dealing with rated power at this power factor level. Is what would be the minimum value of excitation. So again we start with this. So here, okay, one thing one question may comes in your mind, that here we have not mentioned start delta. So whether I have forgotten to copy information, or we do not need that information. These two things can happen. While first one is quite probable, and you people are quite means will be very happy if you can spot a mistake from my end. Uh, but in per unit, do we need per unit means this explicit information about start delta, or in per unit it is like per unit representation, it is actually means it is like not important to consider whether it's star or in delta. Whatever be the value of base voltage, it changes accordingly. So you please think about it and let me know your take. Uh, for the time being, I would like to refrain you from means from doing your celebration. Rather, I insist that I have not made any mistake. Better you people find out that why in per unit representation there is no need to have explicit information about its interconnection, whether it's delta connected or star connected. So here what we are getting is like, now we can write E1 square is equal to actually I'm doing this because there is some purpose behind means expressing it in this form, and I'll show you why the same is necessary. Or we can write Actually, this framing will help us in solving the minimum excitation problem. Right. So now you can see that what is our A is minus IR sine theta, and with this form of representation clearly we can figure out the delta from this, because this is expressed in such a way that this forms the base while this forms the height of the triangle. So we can write that cos delta in addition. What about E naught? Further, this guy is equal to right. So now we can write let us replace this cos delta by this value. So we can write let it be so from this line and this line together, and also using these lines, this using these three lines, what we can write cos delta is being replaced by v plus a e1 plus sin delta is replaced by b by e1. Now the value of actually why we are doing all this, because we are interested to find out the value. Now this value we can figure out from like the graphical procedure. Actually here it is not a linear case, so what you need to figure out from the very first equation and this one, you have to do like or the value of current and voltage, you need to solve it. What I'm trying to say, just a minute. So now it is if we put the values that I is equal to 1, sin theta is equal to zero point 0.6, cos theta is equal to 0.8, xt is equal to 1, xq is equal to 0.8, a is equal to if you put all these values together, you will get that a is equal to like all this. When you put here in the definition of a, where is that? Yeah, here you will get the value of a, b and also the value of k. Let me write it, otherwise you will get confused. Calculated value I am writing using red, and you can see that equation from where it's coming. Okay, so with that your E is becoming, with this calculation result, your E is becoming and E naught will be now here using these two equation, we can calculate different values of, means we will take one value for v, arbitrary values, like say we'll start from point 0.8, 0.9, 1.0, 1.1, 1.2, and we'll calculate corresponding value of E1 and E0 from this. So E1, just put 0.8 here and you find out what is the value of E1 we are getting. It is 1.436. What about E0? E0 you put, after calculating E1 you put here, you will find the value of E0. Then it will be E0 will be 1.614, right? Then you put zero point 0.9 here, you will find it is giving you 1.526, 1.702. For 1 you will get 1.617, 1.790. For 1.1 you will get 1.710, 1.881. For this you will get 1.803 and 1.972. Basically, why I am writing all this, because this is a kind of problem you may not get in normal common book. This problem is a bit boring, but you will learn something that is very very important, that how to form a kind of giving numerical solution to a problem. Here absolute solution is not possible. We be very cautious and apply our numerical whatever we have learned in our numerical analysis here. So we form this green table. Now what is the matter here, for which value, see here it is clear that if we go back to the problem from which we started our discussion, it was given that determine the terminal voltage, means which voltage, it is talking about Vt or V. When it supplies rated current, that means I is equal to 1 at 0.8 power factor lagging with excitation voltage E naught as 1.85. This is problem 1. So we are trying to find out solution of this. So now from this table what we can do, we can write an equation for V, considering them almost linear. It's kind of piecewise linear. Like E naught and V, they are like piecewise linear in a small interval. So we have to pick up the value of V, which is like giving us our the value of E naught we are looking for 1.85. So if you consider this value falls between these two. So for this we can take this V like plus what we should take, that is 1.85 minus 1.79 divided by, this will actually give us the slope, into this will yield So we have answered our first problem, that is rated current at power factor lag. How? Let us quickly revise, because means it was a somewhat kind of unorthodox, you said, the solution method. It's not straightforward. So this is the equation you can write. Then this equation further expressed in this type of form. The agenda, or means sorry, not agenda, that objective behind expressing the equation in such a manner that we are actually looking for this kind of compact form. So once we get this kind of compact form, what and how it is helpful, because unlike normal problem, here P is not stated a priori. Rather, you are about to do it in a reverse way. Like first, the information about induced voltage is given, and then you need to find out the terminal voltage. Generally, what we do, we know the terminal voltage and we go inside to that generator to find out E naught. Here the inside picture of the generator is given, and we need to figure out what you can expect at the generator terminal. That is quite opposite. Generally what we do in case of DC machine, in case of AC machine, whatever, and many other books, generally what we do, we generally go to we go inward, and that is somewhat rational take, in the sense because the outer terminal voltage like Vt is always measurable. But here, why this problem is uh, placed in such a way, because try to understand one thing. Let me share a means background understanding why this problem is important, not because this is means unconventional or unorthodox. Anything, even you can walk on your handstand position, and that would be very unconventional and unorthodox effort, because everyone is walking on their leg and you are walking on your hand. So but it actually you have to understand that how much it's practically feasible, and also that like means people, or the your means whoever will be present there will not bully you, or will not make fun of you, will not will not call police because you are walking on your handstand position, because it's practically feasible or not. Now see here, when you are considering actually two machine you are having, suppose you are having two machine. Now one machine means, suppose when you connect the two machine outer terminal, they will operate, the outer terminal will be at a common voltage. But if you think about that transformer parallel operation problem, we generally used to find out the drop and all other things that may take place in a machine, inside the machine, and that will means during transformer parallel operation were leading us to figure out the value of circulating current. Here also, suppose once you connect many machines in parallel, you will lost individual information about its outer terminal voltage. Whatever you will get, it is the combined voltage across the parallel connection. One voltage will appear across all the machine. So basically Vt will become useless. In that case, knowing E actually give you some sort of advantage, like how much fee you could expect if it was operating in standalone condition. Now for this V, how this could be achieved, and what is the actual power flow is taking place, that is very interesting things. Gradually you will understand more about it when we will discuss parallel operation. And this for this Here we are applying this procedure like E not all these are here. If we when we will solve the next part problem B, you will get more about it, and finally when we will discuss parallel operation at the end, you will get a very clear picture. Anyway, I won't consume much time on explaining the philosophy. So further what we are having here, we are having this chart, and then from this we made this calculation. Then we, since our E naught are given in the problem, we form this kind of table, and then from linear interpolation we find out the result. Okay. Now see the second part of the problem, that is like we can write P per phase power is equal to Vi cos theta. So this yields your I cos theta is equal to P by V. Why we are now forming it in terms of P? Because if you see that the second problem is all about your your rated power at zero point 0.8 power factor lagging. So rated power is mentioned. So that is very interesting. Now so, and accordingly you can write that so again let us write that expression of E1 square is equal to from our previous expression, from this expression, now what we can do is that we can replace this I cos theta by P, right? So we can do what? We can replace this I cos theta by PVR, and this one by tan theta, right? Similarly here, so this will become the equation. Now similarly like the previous case, we can write it like E1 is equal to root under V plus CV square plus dV square. What is CV and dV? Your C is equal to R plus R plus x cube tan theta into p, and d is equal to xq minus r tan theta p, right? So, and accordingly you can write also cos delta, just like the previous problem. It is v plus c by v e1, and sin delta is equal to d v by e1. Now what you will be having here is that e naught is equal to into, let it be k. So this will give you something like, I'm not doing the intermediate steps because you can do it. Right. Now here we can have this like, okay. Now if you just calculate the value, because now here p is given. What is p in per unit? P is 1, and theta is also that cos inverse 0.8. So from these two, and also r xq are given, you can figure out the value of cd. What you will find that c is equal to, this is again calculated, c is equal to your 0.61, and d is equal to 0.7925. So that gives us, okay, I would like to mention that this is a 50th page of our this this second semester. Already I have myself written 50 pages. Now you please check how many pages you have means filled up. Obviously, my font size is very large, so obviously, if you are having a smaller font size, that is okay, but it should be minimum 2 to 3 times of mine. So, if I assume that your font size is half of mine, then also you should consume 50 pages in writing electrical machine stuffs on your own personal copy. Otherwise, it's completely pointless. So, doing that, you'll get some value. this is what we are getting. Now let us do that calculation. We will take many values here. Is there any table available? No. So just let me draw a table. Uh, Here this is V E 1 and okay. So for V we are having here values like 0 0.8, 0 0.9, 1.0, 1.1, 1.2, 1.3, because high value of your E naught is given, and this time it will not be very easy for us to figure it out, so we need to take a lot more values. Just a minute. So this will become 1.794, then the third one will become 1.805, then this will be 1.832, then there will be 1.871, then it is 1.921, 1.979. Now, okay, let me write E naught, because those who want to learn, they may get a lot of things to discuss here, to ponder upon this particular fact, but it is your choice. Like, I do not want to grind you with the burden of assignment. I think whatever I have written, and if you calculate, means consider my calculation is not incorrect, and means obviously I might have made mistakes in a few places, but for most of the cases, I don't think my calculation is incorrect. Now, for this, you can think that what is happening here. See, our that this is increasing V. V is linearly increasing. What about E1? Suddenly a droop here in this region, in these values. If you consider these values, see 1.85, then 1.907, then this. So things are pretty surprising, isn't so? You have to figure out that what is wrong with this Now here one thing, another very uh, is what I could say that is very interesting to see that we are having like 2 points for which the E naught is same, almost same. The two terminal point, like if you take this segment and this segment, the investigation was started with an objective of finding the value of V when E naught is 2.1. Now both these are satisfying this one. So how to proceed? That similar linear approximation, we can take one here at this end. Another one would be from this side. Oh, well, just a minute. This must be the slope here must be negative. Yeah. So this calculation, just a minute. Let me check and do. Okay, no, no, no. I was correct. Not there is no such problem because this range is falling in between. Like this V must be somewhere in between. So 0.852 is perfectly okay. And then the next one, that is 2.11 minus, sorry, here it must be. Now, which value of V we will be getting? Like in our terminal, we cannot have two voltage values. Who will decide? Huh? Think about it. Who will decide? Two voltage values we are getting like for E naught, that is 2.1, we are getting two voltage values. Which one we can actually get? Perhaps I think you should read the problem once again and then to figure out what is there. Now for the given power and power factor, the last portion, that C, what is the minimum value of E naught? Minimum value of E naught from this table you can spot. Minimum value of E naught is this gentleman. This whole calculation is done based on particular power and power factor. So only choice of minimum E naught is your E naught is equal to, this is the minimum value. Okay. I do not know whether any one of you are watching this video till this end or not. But if you are watching this, then you will and you try to figure out the reason, you will be getting a lot of things to learn here.